So hello, everyone. Today, we're very happy to have Han-Sang Kang, who is an assistant professor in the Department of Statistics at the University of Wisconsin-Madison. So Han-Sang from 2015 to 2016 was a postdoc in economics at the Stanford Graduate School of Business and advised by Guido Imbens. And in 2015, he received his PhD in statistics from the Wharton School at UPenn. He was co-advised by Tony Kai and Dylan Small. So Han-Sang's research is focused on developing theory and methods to analyze causal relationships in large observational studies by leveraging instrumental variables, econometrics, high-dimensional inference. He is interested in application to genetics, epidemiology, health policy, education, and economics. So Han-Sang's talk is titled Assumption Lean Analysis of Clustered Randomized Trial in Infectious Diseases. Han-Sang, the floor is all yours.
All right, thank you for the introduction, and thank you to the team at University of Washington Biostat for inviting me and organizing the talk. I'm happy to be here today. So today I'll be talking about assumption lean analysis of cluster randomized trials in infectious diseases. This is joint work with my student Chen Park, as well as, and this started off actually with another work that I've done in the past about cluster randomized trials, and it's now morphed into something, and it's also timely in the sense that when we were working on it, COVID kind of hit. And then I hope, and again, feel free to stop me if you have any questions. I'm unfortunately not able to see the chat on this full screen mode, so if you want to just interrupt me whenever there's a question that you want to want me to answer. So roughly the outline of today's talk and the problem statement is as follows. So most cluster randomized trials in infectious diseases have this following stuff. So the one that we're focusing on is did face masks and hand sanitizers prevent spread of the influenza during the 2008 flu season in Hong Kong. So this study came from Cowling et al. In 2009. And we also looked at other CRTs in infectious diseases by various authors. The paper that's associated with this paper, we summarize the literature specific, and we noticed a couple of things about the CRT, specifically the analysis side. So the first thing we notice is that when people estimate ITT effects, which is often the primary first target estimate that they look at, they often use parametric mixed effect models to model clustering or dependencies between units in a cluster. So what do I mean by this exactly? So if you have J clusters and NJ units in a cluster, and let's say YJI represents a binary outcome, let's say whether you got the flu or didn't get the flu, or whether you have COVID or you don't have COVID, and let's say ZJ represents a cluster randomized treatment or some kind, and XIJ is some covariates of that person. So oftentimes, if it's binary model, people would assume this type of model, a general linearized model, general linearized mixed effects model where you have logistic with alpha J representing a cluster effect. It could be random or fixed. The beta ZJ, where beta represents the treatment effect. And to incorporate covariates, they use this kind of linear form. We have X transpose Xij. Now, the other thing that we notice, this is more on the theory side of things, is that when you prove asymptotics about this, especially when alpha J is random or even fixed, they assume that the cluster size is bounded off to the case. And this often means that this means that whatever asymptotic normality and inference that comes out of it is applicable to CRTs of small clusters. So households are very, very small villages. And the other thing that we notice is that very few CRTs actually, I don't think we have seen any CRTs that look at spillover effects that happens due to non-compliance. So I'll talk about what exactly this means in a couple slides from now. So the goal of today's talk is to address those two questions. Specifically, we're going to analyze the overall and heterogeneous ITT effect in a way that we don't need to assume a model for Y. And this is similar to a DR estimator. And it's a modest extension, really, it's a modest extension of Ding et al. To cluster setting where the units may have dependencies. And one key thing that we notice is that it's actually invariant to affine transformation, and something that I think people in CRT, anytime that people deal with clusters, should actually think about. This is not so much a problem in IID data because most estimators that we know and love in causal inference, diff and diffs, AIPW, IPWs are all affine invariant, but in cluster settings, that's not always the case. And finally, for theoretical things, we allow NJ, we can allow NJ to go to infinity. The second part that we're more excited about is actually a brand new method to bound spillover effects among subgroups. And specifically, what we do here is we use machine learning to actually build a classifier that may not be perfect, but we use this imperfect classifier, possibly wrong classifier, to tighten the bounds for the spillover effect of interest in a linear program. And one of the nice things about this approach is that it's completely model free, as in you could use any machine learning classifier. It doesn't even have to be a consistent machine learning classifier, and that it estimates consistently the true functional form, and it'll still cover the true bound. It'll still cover the true effect of interest. It'll produce a sharp bound. And what we were more surprised was that when you actually apply this in practice, it had almost a 50% reduction in the bound length. So if you ever worked in this literature or bounding causal effects, you notice that the bounds are often very conservative, and it's almost, you have to hope for good data. But when we applied it with our new method using machine learning and a linear program, it dramatically shrink the bound by a lot, and it might be actually of use down the road. And specifically, in addition to collecting and hoping for good data, PIs can now use machine learning and other classification techniques to actually tighten some often conservative bounds in practice, and maybe bring back bounds as a way to estimate or get some idea about causal effects. And I think this actually I'm almost certain this has broader application policy identification, especially using ML-assisted ATE to bound with an IV. The reason we call it assumption lean is because we don't, on both methods that we propose, but with both analyses technique, we do not assume a correct model for, in this case, Y, or in this case, really a correct model even for the machine learning classifier. And we use standard assumptions. I'll talk about what those mean. And we also try to avoid extra assumptions for the sake of point identification, especially for the part 2, where, let's say if you wanted to identify the spillover effect, people might assume more things just for the sake of point identification. In our case, we say, okay, let's not make stringent assumptions, and instead of making stringent assumptions to point identification, let's make less stringent assumptions by using machine learning to actually tighten the bounds that are already there from the assumptions that we have. And this is the philosophy that Mansky and Pepper suggest in their seminal paper in 2000, one of the seminal papers in 2000. And then we use our techniques to do some simulation analysis, reanalysis, the Hong Kong study, and then some guides for practice down the road for CRT and people analyzing CRT data in infectious diseases. So the motivating example that will kind of motivate the talk is, did face mask and hand sanitizer prevent spread of the flu? And so Cowling et al. Did this study during the 2008 flu season. And if you know a little bit about pandemics, this was right before the swine flu hit pretty badly in Hong Kong in 2009. And so the timing was quite perfect even for Cowling, who was actually designing the study. So what did he do? So he enrolled households where one member had the flu, and this is commonly known as an index patient. And then he measured the covariates for each member in the household: age, sex, prior vaccine status for the flu, how big is the household, how many people live in the household, and so on and so forth. And then 72, roughly half of the households were randomized to get free masks and hand sanitizers, and this we'll call the treated group. And the rest of the households got nothing, so they didn't get the free mask or hand sanitizers. And then after randomization, they went back and then they record the flu status of everyone. And this entire thing, from enrollment all the way to recording, happened within a 36-hour period. And here, YIJI equals 1 means that this person has the flu, and YJ equals 0 means they didn't have the flu. By the way, they also recorded flu status a week later as well. But we're gonna, any case, the key steps in the author's analysis. Obviously, if you'd ever publish anything about randomized trials, you need to do a covariate balance table, and then they have this, and then they show that it was balanced. And what we're curious about is how they estimated the intent to treat effect. And in this case, they, as I mentioned earlier, they used just a difference in means, and then they used cluster bootstrap to essentially get the uncertainty estimate on this. And when they wanted to incorporate covariates to tighten their estimates a little bit, they used a logistic mixed effects model, or they actually also tried cluster bootstrap with a fixed effect as a robustness check. And then when they did these type of analysis, they found that the ITT effect is significant, and this beta here, based on adjustment of covariates, is also significant. That is, giving free face mask and hand sanitizers did prevent the spread of the flu in either OR scale or in a linear difference scale. So some comments that we noticed when we read through this analysis, and it is our opinion that most CRTs in infectious disease settings use similar analysis plans, and we again have a review section entirely dedicated to this. In particular, what we're interested in is how they model clustering, how they model the fact that the people are dependent with each other, especially if they're in the same household, and how they model that behavior. And especially in the analysis ITT effect, they often assume parametric mixed effect models to adjust for covariates and to obtain the estimates. And then if they wanted to do like a heterogeneous treatment effect estimation, either they would do a subgroup analysis where they would partition the population based on X, or they add an interaction effect for the heterogeneous covariates. So what I mean by this, they would either, let's say if X is discrete and they were only interested in one value of X, they would just take the difference in means between that particular value of X and use cluster bootstrap for uncertainty estimates, accounting for dependence, supposedly accounting for dependence. And, or if they wanted to use like a covariate adjusted one, they would have an interaction term between X and Z, and then estimate this psi parameter along with beta. This will be the main effect, and this will be like the interaction effect that we teach in our courses. And for the cluster level effects, it depends on who you read, but sometimes it's assumed to be fixed, and they would use a cluster bootstrap or sandwich estimator, or if it's random, they would use like a variation of likelihood-based principles to estimate the uncertainty. And so this is one aspect. The other thing that we notice is that spillover effects are induced by non-compliance are completely not analyzed at all. And so let me discuss what that means in this slide. And so after cluster randomization, some people in that original mask study did not use mask, and they note this in their appendix table. Specifically, 27% of individuals in the treated households, that is the households that got free mask and hand sanitizer, actually used them. So the rest of them, about 73%, did not actually use the free hand sanitizer that were given. And 8% of the individuals in the control household actually used the mask. So they were not given the free mask and hand sanitizer, but they actually went out and got themselves one in the process. So if you roughly divide this, and you kind of have to weight it by the size of the cluster, but it's roughly about 19% compliance rate. So even if you gave the free mask, there's a 19% chance that they're actually going to uptake the treatment. But what's interesting here is because of this heterogeneity in the compliance, those who are masked actually may protect others who decided not to wear them. And this is essentially a spillover effect among people, mask wearers to non-mask wearers, and non-mask wearers being the vulnerable subpopulation as we define it. So just to visually illustrate what this means, suppose you're living in a household that was randomized to get free masks. And after initial randomization, the top 2 people decided to use this opportunity to actually wear them, and the other 2 people, bottom 2 people, decided not to wear them. The question here is, can mask wearers protect those non-mask wearers from getting the flu? And that's the spillover effect among a vulnerable subpopulation, because the effect from the mask wearers is spilling over to those who are not wearing masks. And obviously, if the spillover effect is positive, that means that the wearing mask protects non-wearing vulnerable individuals from the flu. And if tau and t is less than 0, that means that wearing masks are harmful to others who are not wearing the flu. And we don't think this is likely based on how we know about the transmission of the flu, but this actually helps us even tighten our bounds further, as we will see later. And more generally, we'll talk about this later down the road, but knowing the plausible range of this may inform public health policy about susceptibility of a disease and maybe even herd immunity among a certain type of population. So other things, this is not only specific to masks. In fact, in vaccine CRTs, you can ask the similar set of questions in that some people simply can't vaccinate it irrespective of the treatment randomization. They might be immunocompromised, pregnant, they might simply refuse. They might be allergic to the vaccine, or they might be too young to actually get vaccinated. But those who can get vaccinated may actually protect those who are vulnerable from getting vaccinated, when that could be a spillover effect among a vulnerable subpopulation. The other one that I'm more familiar with is a malaria control, specifically looking at how distributing malaria insecticide-treated nets help prevent the spread of malaria. And these nets, just if you're not familiar, are essentially bed nets, but they're treated with certain chemicals so that when the mosquito lands on them, especially mosquitoes that spread the malaria, they'll be either killed on contact, or usually they won't be able to spread the disease. And so some good, well-known economists did some experiments to look at the effect of this, and by actually randomizing the subsidy, the price subsidy of ITNs. But even if some households receive these coupons to get these nets at a 50% discount or 75% discount, or even at free, some households simply did not buy them, or not even after buying them did not use them. But these households who did not buy them or use these ITNs may still be protected by households who are using them, because these nets are designed to kill or disable mosquitoes on contact, and thereby limiting the spread of malaria. Now, this, because I was familiar with example 2, and I was interested in this question in general during my postdoc years, with Luke, we showed that this effect, this spillover effect and other network effects cannot be point identified. Essentially is a theoretical limitation of a CRT to study any kind of spillover effects in general. And we theoretically that whatever data generated from a CRT, typical standard CRT, you won't be able to estimate, point identify the tau and T. Now, in the paper, in the original version of this paper, we suggested that perhaps if you know enough about the disease and how it spreads, you can maybe model it and then get away with the point identification through a model. But in this work, we actually decided to partially identify this by providing a plausible range so that we don't have to rely on a particular model for how disease spreads as a way to do this. But we can use that model to actually help us tighten the bounds further. So the first part of the talk is just the analysis of overall and heterogeneous ITT effects. Again, we're not doing any groundbreaking work, in my opinion. It's just a modest extension of existing work. And just to point out something that I think is ignored in CRT analysis CRTs that should be not ignored, especially in regards to affine transformations. So just as a notation, you have J clusters and NJ units per cluster and N total units. Observed data, ZJ again is the cluster level randomized treatment. AJI is the unit level treatment to see whether they actually use the cluster randomized treatment. YJI is the unit level outcome, and XJI is the unit level covariate. So this could be whether you had the flu, and this could be age, sex, and other things that describe the person. Potential outcomes, I've been told by Marco that you guys have a very strong, not only theoretical team, but also very good causal people there. So you have the AJI, which is the potential treatment receipt when unit JI has some treatment ZJ. You have the potential outcomes of the unit JI when their cluster randomization is ZJ, when their own treatment receipt, unit level treatment is the AJI, and the vector of your peers treatment receipts. And if you're familiar with the causal inference literature, this is actually known as interference because your potential outcomes now depend on your peers treatment receipt. And there's this thing called a natural potential outcomes where essentially it's this thing, except instead of setting the value to be AJI, you set it to be their natural potential receipt from the treatment and just replace that as well. From this notation, it's fairly easy to define what the overall what a familiar estimates, a formalized familiar estimate. So the overall ITT effect is essentially just the sum of individual level ITT effect TJI, where TJI is just the contrast of these natural potential outcomes. And the heterogeneous ITT effect, excuse me, is defined, it was actually defined by Ding et al. In this particular format, is some parameter beta that satisfies this form. Actually, I think Semenova and I think Chernozukov also had a similar version for the non-finite sample inference setting. But in any case, it's essentially just how far is the individual level treatment effect away from X transpose, Xi transpose beta. And this, if you solve it, turns out to be this. And just to be clear, this is the best linear approximation of TJI, as Ding et al. Extensively discusses. This does not mean that the individual ITT effect is a linear model. In fact, this entire individual effect could be nonlinear, and the residual of this may have non-zero mean, unlike your usual typical linear regression exercises in maybe undergraduate courses. So essentially, this beta, it represents the best linear approximation of something that could be nonlinear. So based on this, if you were to follow Ding's strategy, or pretty much the strategy that has existed since the 1920s, one way to estimate this is by what are known as name and style difference in means estimate, or just a simple difference in means estimators, where you take the difference between the treated and the control. And the same thing for this, you can kind of rewrite this and following Ding to be written this way. And you can show that this is well known to be unbiased since the 1920s, 30s, long time ago. However, what's not so well known is that this estimator is not invariant to transformation in clustered settings. So what do I mean by this? In non-clustered data, so in IID settings, if you were to take the original outcome and transform it just by, let's say, a simple linear transformation where we add something and then multiply it by constant, then the estimate and the estimator, let's say the IPW, AIPW, or even outcome regression, satisfies this very simple inequality. The new estimate based on this new outcome is just proportionally related to just B times the original estimate and the original outcome scale. And the same thing for the estimator, the new estimator based on using the new outcome, observed outcome will be just a proportional to b times the original estimator based on the original outcome. And that would also mean that regardless of what units you're in, let's say if they're in linear affine transformation units, the p-values for testing whether there's a treatment effect or not will be the same whether you use the new y or the original y. However, in cluster data, this property does not hold. And this was a surprise to me. And I only discovered it when you're recoding the data set for analysis, and that we recognize that this doesn't hold for name and style on difference in means estimators. So how do we discover this problem? So original data actually had the binary flu case flipped as like 0 would be you had the flu and 1 would be you didn't have the flu. And so we recoded to something more, something that made sense to us. And then that actually just turns out to be just a linear transformation in this form. But if you do this, we expected the estimand flips in sign as expected, as in because we flipped the y, we expect the estimand to flip in sign from the original one. However, the estimator, if you were to just use a difference in means estimator, does not flip in sign. And what's more troubling is that it is actually significant under one transformation, but not significant under the other transformation, even though all we did was simply recode flu status from 0, 1 to 1, 0. And this was troubling to us. And to the best of our knowledge, I don't think people have really discussed this in the context of really difference in means estimators and cluster randomized trials. And there's another measure in this data set measuring fever, what was your fever? And then if the investigator were to convert this to, from Fahrenheit to Celsius, you may face a similar problem. So given this minor discovery, but I think minor yet important discovery, we decided to, okay, let's actually develop another estimator, or we'll use a different estimator. And our idea was to forgo unbiasedness. There's a fixation in finite sample inference for unbiased estimators. And so we say, let's forgo unbiasedness in favor of an invariant estimator. That is an estimator that is invariant to affine transformation. And so this is essentially it. In fact, this is not even of our own making. It's been around since Cochrane day. This is the Cochrane's, I think, textbook, but it goes back way back then. But this is the estimator itself. And one of the nice things about this type of estimator is that this estimator is invariant to affine transformation of the form of this type. That is, if I were to create a new y variable based on just a linear transformation of the original variable, my estimand and the estimator flips as expected. And that's a good thing for investigators. And more importantly, even though it's not unbiased, under causal consistency and the cluster was randomized to treatment or control and other mild CLT conditions that are pretty much the same as the one in Ding, you get that they're asymptotically normal and centered around the right point. And the key point here is that while these estimators are indeed biased in finite sample, they are not only consistent, but they have the same asymptotic variance as the usual Neyman estimators in the Ding et al. And the Fogarty et al. And so there's a minor theoretical note that I also want to point out is that typically when people do this exercise, actually when Ding did this exercise, he assumed that the NJ was bounded, but we allow this NJ to possibly go to infinity as well. And also Ding's estimator, as we mentioned, is even asymptotically, it's not even invariant to affine transformation, especially in cluster settings. And in non-cluster setting, this is not a problem, but in cluster setting, this becomes a problem. Okay. All right, so I will stop here to take any question before I move on to part 2, if there are any questions.
I guess I had a quick question. I was wondering if you could provide some intuition for why the first estimator is not invariant to the transformation, because that also seems very surprising to me. And
yeah, it surprised me too. I asked my graduate student to flip this, and then I was like, why are we getting different p-values? Is it a finite sample issue? And so the key insight is that the size of the cluster is actually also a random variable, if you think about it very closely. In IID settings, there is no notion of size of cluster because everyone has their own one-person unit. But in cluster settings, you might have treated units where their distribution of cluster size may actually be different in finite sample than the control group's cluster size unit. And that's actually where the invariance no longer holds. And that's really the key reason. is that NJ, the number of people per cluster is actually maybe different, actually is almost always going to be different between the treated group and the control group in finite sample. And that difference may persist even if you go in asymptopia, unless you control for it in the right way.
Thank you.
Yep. And just to add to that point, that's why in our new estimator, we have this NJ. Now the clusters who are treated now are weighted by the number of people who are in that cluster. And that small change essentially makes this now invariant, makes it invariant. Alrighty. So the second part of talk is about the spillover effect. So among a vulnerable subpopulation. So this, the takeaway point here is we essentially provide a new approach of obtaining sharp bounds in this problem using machine learning and linear programming together. And this is a visual illustration of what's happening, and I'll illustrate how we get to this visualization. Essentially, what happens is if this is a true effect, and this is the linear program that constrains where the true effect should be, what our method does is with the machine learning, it can actually make this constraint a little bit smaller, or actually sometimes drastically smaller, and have tighter bounds for where the true effect might be located. And that's roughly the high level idea. So brief review of non-compliance of CRTs. Effectively, units in a cluster may or may not take the randomized cluster level treatment or control, and they might do so in a non-random manner. And this has been studied very extensively culminating to a very seminal paper in the mid-1990s, where you can divide up the population into 4 groups depending on their compliance level. So you have the always takers who would, in the example of the masks, they would always wear a mask irrespective of cluster randomization. Compliers who would only wear a mask if they were offered a free one. Never takers would never wear a mask irrespective of whether they're given free mask or not given free mask. And the defiers would be the complete opposite of compliers. And usually the target estimand in this case, again, without interference, would be in the complier average treatment effect. And there's a lot of work in this area, some of which I've even done in the past. And then typically assumptions that people make to identify the complier average treatment effect is as follows. You usually assume the causal consistency. The observed outcome is one of the potential outcomes, that the cluster is randomized to treatment or control. And then the treatment adoption, that some units actually decide to use the treatment if offered. The exclusion restriction, that the outcome of U is only dependent on whether you actually use the treatment or not, and not dependent on whether you were initially randomized to the treatment. And monotonicity, that there's no defiers in the population. And this could be enforced sometimes by design of the study. And the only thing that we make to these standard assumptions is just some minor modification to allow for interference. Specifically, we changed this to, instead of having it only depend on you, it now depends on peers. So the potential outcomes, again, from the couple of slides back, now depends on not only the cluster level treatment assignment, your own treatment receipt, but also your peers treatment receipt. And your potential outcomes as a function of all these 3 variables. So we essentially extend the notation, and then subsequently we also extend the exclusion restriction to say that it doesn't matter what your cluster level of treatment was, as long as you fixed your treatment receipt as well as your peers treatment receipt, your potential outcomes will be the same. And so that's the only thing that we extend from there. Exclusion restrictions always talked about in terms of plausibility and unplausibility. This is definitely in the context of our case about the mask. This is implausible if the cluster randomization itself changes the unit's general hygiene. That is, you got your free mask, and that made you more hyper aware of your surroundings, and therefore it changes your behavior. It changes whether you get the flu or not, compared to if you weren't offered a free mask. And this is definitely something that one should be aware of in this study. But it's also, there's a recent paper by Michael and Betts, and then I think their student, on how this could be plausible in certain settings, especially in blinded settings in some vaccine CRTs. The one additional assumption that we make, because this seems very plausible in this area, and also you can even tighten the bounds further. We don't have to assume this to tighten it, but is that the outcome is bounded and monotonic. As is, actually, we need the boundedness, but the monotonic is not necessarily necessary. But so the outcome in our case is whether somebody's infected or not is bounded, and the treatment is not harmful. So the outcome variable is bounded between 0 and 1, which in the binary case it is, and if it isn't, bounded, we can always scale it to 0, 1 to satisfy the boundedness condition. And the outcome, the treatment is never harmful, that is wearing mask is never going to be harmful than not wearing mask. And so this monotone outcome seems very reasonable in our case. And in fact, this assumption, a variant of this assumption has been used by Choi in 2007. And it's fairly plausible for the Hong Kong study and some other, I would say, where the product of interest is trying to prevent the spread of a disease. So a couple of network effects. As I mentioned, my earlier work said that this, with these assumptions, is still insufficient to point and identify most meaningful network effects that people might be interested in. The original version of this paper suggested that we make a model on, because some diseases people may know how the disease spreads, and you can treat that as known and truth. The form of the model is true, and then point identify. Recently, my thinking has changed over this, and I think the better approach is to use this as a working model and then actually sharpen the bound instead. So not take this as a truth, but use it as a working model to sharpen the bound, so you make less assumptions. So here, this paper focused on spillover from a vulnerable cell population, never takers, but you can also do this for always takers and compliers as well. So again, the estimand formally written as is this thing here, and remember the spillover effect was essentially if the household got treated with masks, some people wear them, some people did not wear them, and you want to know whether mask wearers will protect the non-mask wearers, essentially. And this is the effect that we're looking for at the end of the day. And that's the green thing, that's is mathematically expressed as this form here. Keep in mind that this little term here, which we'll talk about, the fact that it's only summing over never takers. So how do we bound this quantity, green quantity? The first thing we do is we predict whether you're a vulnerable person or not with a classifier. And this classifier is essentially for some function. This classifier has a particular form. For some function f theta that takes in covariates and spits out a real number. We consider classifiers of the form where essentially if f is called a learner in our setting. If the learner is greater than some q, then you're classified as an NT. And if it's not, you're classified as not an NT. And that's how a form of the classifier, our form of the classifier. Now, this classifier may look restrictive, but as I learned over the past 2 years, apparently this is the last step in a relative deep net, especially if you're classifying. This is also an SVM of F being the kernel and Q being the margin condition. And then in Kennedy's paper, Edwards' paper some time ago now, this is also known as a quantile threshold classifier. In econometrics, this is also known as a binary choice model if you modify this a little bit slightly. And so this is not too restrictive as it actually encompasses these things. And the key point here is that this classifier does not even have to be perfect, and it will still cover the target estimand of interest. And in fact, this classifier will never be perfect, because if you know about this literature a little bit, you'll never be able to know never taker status for everyone simultaneously. And in the worst case, the classifier could be completely random, but a good classifier for low misclassification tighten these bounds in tau NT. And that's why we say that, I'm not a machine learning expert, but some investigator who can improve this classifier with newer and better machine learning methods in a risk-free way, because regardless of what classifier is given, we will still be able to cover this tau NT. And so it's never harmful to improve upon this CN at the end of the day. And compared to some other works, where you need to have a correct model for the classifier to get anything reasonable. Here, we don't make that assumption. Essentially, you can do whatever you want, and our LP linear program at the end will still be able to cover this. And if you do it well, it will even have much tighter bounds. And then so that's the second part. So once you have a classifier that you're happy with, and it has to be of roughly this form, you use it inside of a linear program. And this is fairly standard if you worked in the partial identification literature. Essentially, use the restrictions from the standard assumptions about the monotonicity, and then you use the CN as the imperfect classifier and the indicator function that I briefly highlighted in the previous slide. And just to give context, in the IV literature, most IV bounds, I don't think, do not use any covariates to tighten them. Although I think this last paper by Sonia actually says that we should, but they never really discuss how to. And so this could be a way to do that. And in the interference literature, to my knowledge, and again, to my limited knowledge, I think we are the first to use IV to bound spillover effects in the treatment. There's some related work by these two folks, but I don't think they're definitely using machine learning to get this bound. So how do we train a classifier for never takers or the vulnerable subpopulation? So just as a brief notation, we're just going to denote NTJI to be one, a variable, binary variable that takes on value 1. If you're a never taker and 0 otherwise, you have some, and then the rest is fairly standard. You have some loss function. It can be squared error loss, logistic cross entropy loss, or some penalty. You have some learner, you can have a linear learner, kernel SVM, whatever your favorite one is. And then we're going to train this classifier, this form, by solving a constrained risk minimization problem. So you're going to have some loss function. You're going to try to get the learner to be close to this binary classification status, and you're going to constrain it so that this particular constraint holds. Now, just as an example of what classifiers fall under equation 1, you could have a linear learner. So you could have a linear summary of covariates, and then you can use a square error loss, even though it's binary. That's perfectly fine. You could have a logistic learner with some kind of logistic function, and then you can penalize this because maybe you think this is high dimensional, or maybe of moderate dimensions. Of some lambda, you can have this particular lambda penalty. Okay. Now, if you been in the machine learning literature or if you're familiar with this literature, machine learning literature and classification in general, if you're given this problem initially, you recognize a couple issues. One of them is that this Q star solution that satisfies this constraint here may not exist in finite sample. And that's partly because of the fact that there's an indicator function. There might not be essentially a separating hyperplane in the SVM terminology. The other thing, this is more of a, if you're on the computational side of things, is that if you ever wanted to actually solve this, you need to optimize over an indicator function, which is not smooth. And this provides both computational and later on uniqueness issues if you want to do any theory about it. And then this is more causal. In causal inference, it's well known that you can't observe never taker status for everyone. You only observe, and so you can't even train this because you don't even observe this for every I and J. And so the next slide talks about high-level overview of how we fix this using techniques from machine learning, actually. So one thing that's underappreciated one thing that's not often used, but sometimes used in machine learning, is to add a little bit of noise to your learner and to use the randomized learner to actually help improve prediction. And this has been discussed in the earlier papers in Sistema and DAO in 1991. And I think Goodfellow in his book goes into detail about this procedure. So what we do is we do the exact same thing. And partly because this Q star may not actually exist, we actually add a little bit of noise to it by some uniform noise. The choice of this noise does not matter as long as the radii satisfy certain conditions. And then now this Q star will have a solution. And if you're familiar with SVM, essentially what we're doing is we're actually extending the margin a little bit so that we now have a separating hyperplane that actually can separate the data set. EJI can be any distribution, but the only constraint that we need for theory is that the radii of this noise, so how big your noise is, it needs to be over 1 over J. And we're going to call this classifier to randomized learner to be C tilde. As for the indicator function, this portion, how do we optimize our indicator function? Well, this is, again, used in the machine learning literature, but also used in optimal treatment regime literature. We're going to use a smooth surrogate to smooth out this. Now, when I asked my graduate student that we can just use any smooth surrogate, he wasn't satisfied. So what he did was he came up with his own smooth surrogate indicator function of this type that's parameterized C and T. Nice thing about this smooth surrogate is actually that this is not only smooth, it's not only continuous, but it's also differentiable. And that differentiability actually helps us do inference down the road at the end of the day. Whereas some of these other smooth indicators, we weren't able to, or he wasn't able to show whether it was worked or not. But theoretically, it's probably possible to use more common ones like hyperbolic tangents or logistic. For the choice of this indicator function that we developed, surrogate indication function we developed, the C and H just needs to be of a certain order of this type. And then finally, the last solution about the fact that we don't observe NT for all the IJs. If you if you do in treated clusters, we do have some idea what their NT status is, and so at a high level, we just train the classifier on the treated clusters. And so ultimately, what this boils down to is the original problem becomes this problem, which we can solve where the indicators from function replaced by a surrogate indicator. We now have a randomized learner instead of a deterministic learner. And then the estimated classifier, we just call a C tilde with eta hat on it. Okay. Now, once we have the classifier, then we put it inside an LT linear program to bound the tau and t. So to do this, first we just define what it means to be having a good classifier. And so we're going to just define an overall misclassification rate between how many times does the true NT status match up with, does not match up with the classifier's NT status. And then the big picture idea is essentially use this classifier that we built to predict whether someone's an NT or not, and just do a plugin for this and to get an initial estimate of this estimate, even though it's not a partial point identifiable, we plug it in anyway to get an initial, possibly bad estimate of this thing. And so if you recall, this tau NT is of this form, where you had some y's and there was an indicator and there was y0 an indicator. I separated into two pieces, but you could combine them together. It'll be y1 minus y0 is the indicator form. And what we do is essentially replace this indicator with what we trained from actual data, and then effectively we use this as like a warm initial start of where this may be potentially located. And then that's essentially our LP step. Essentially, the LP finds, based on tau C, which you can estimate, which in our paper show we can estimate from data, and this one we can't point identify. We use the LP to find the worst case distance from tau C to tau NP. And the LP constraints are essentially constraints from the assumptions as well as the misclassification rate. How well did the classifier do? So this is a picture overview of what this means. Suppose the true NT effect is here. We have an estimated NT effect from the classifier. And what effectively this LP is doing is this big bound here, the blue dotted one is the bound that essentially comes from the assumptions A0 to A5. This dotted square is the bound that comes from how good your classifier is. And when you combine the two in the LP, you get this green bound, which essentially tells you roughly how far is the red thing, worst case distance between the what we have as the initial NT estimate from the true value. It could be far away from here, it could be far away from here. We only, in this diagram, we know exactly where it is, but in real life, we wouldn't know where this red point is. So we essentially think about in real life where we don't have these red points, and then we construct this, and we know that this green region is the worst possible, the possible region that the true NT could be in. And that's how essentially our LP works. Another way to think about this, I think is useful. The actual LP is in the paper, by the way, is that think of this as the initial start in a gradient descent algorithm. And then essentially what we do is use the LP to figure out the worst how far is our initial value away from the true value that we're trying to reach. And what is the worst case of that thing? And that's essentially what our LP does at the end of the day. And so some properties of the LP, under some standard assumption, the LP has the following properties. Given whatever classifier you give it, the solutions will be always the tightest possible bounds given that classifier. Not only that, if you ever worked in linear programming, you realize that not every solution has a closed form. In this case, we do. The minimum and the maximum of tau and t has this fairly simple form. And the plug-in estimates, which you can estimate, are consistent for under some conditions in F and L. And just to interpret this, what does this mean? That means that without any classifiers, or if a classifier has 100% misclassification rate, that means that the tightest possible bounds on tau NT is 0 to this one value, tau 1 NT here. However, as the misclassification rate goes down, and so as our classifier improves in prediction, our classifier gets better, and ultimately we can show that the upper bound equals the lower bound, which then means that we have point identification. And more importantly, for any classifier we have, tau and t will still be in the bound that's produced by the LP. And for inference, one thing that I asked my student to do is to spend a lot of time on 2. Because once you know the closed form of this, then we can look through more recent developments in how to do inference for partially identified sets and figure out which one of our bounds fall under this. And thankfully for these type of max mins, one max, one mins, Romano and Shishik has a very interesting, it's a very simple procedure to do this. So we just directly apply this, because this thing effectively this thing is a, you can, we, under some condition, this essentially satisfies the condition of Romano-Shishik for us to do simple essentially cluster bootstrap. So some in the interest of time, I mean, I can go through the simulations, but ultimately, in any simulation, our thing is good, and competitor is bad. That's pretty much it. But I think the more interesting part is the analysis of the Hong Kong study, so the actual study. So this, with the controlling the spread of the flu. So effect, if you use the affine invariant method that we talked about in the first part of the talk, is indeed significant, and the confidence, I mean, there's in the tinier ranges. And we also looked at the heterogeneous treatment effect that's in the covariate space, all the way from gender to, I think, various things, household size, how big the household is, and index patients' characteristics, and so on and so forth. And one of the things we noticed is that these two coefficients are significant. So how do we interpret that? Oh, sorry, before we interpret that, if you've done this a little bit, and I haven't done it in a long time, I haven't done it I don't have too much experience in it, but apparently there's different ways to code how big your cluster size is, depending on this model for disease. So we actually looked into this very old papers on models for disease to encode cluster size as a way to do this. I was actually impressed by the amount of work that's done in this literature on just how to measure spread of a disease based on the size of the cluster. But so we use some of these principles when you're doing the ITT effect. But in any case, the overall ITT effect is significant, and this actually agrees with the original study. Remember, in the original parts of the slides, where they also found that the giving hand sanitizer-free mask helped reduce the flu cases, and in our case, in the linear scale, it reduced flu case by 7.8%, and it's significant. Also, we found that the heterogeneous ITT effect is significant. The original study actually didn't do this, and in particular, if you look at these two coefficients and interpret it and try to make an interpretation out of it. Effectively, what this means is that giving free mask and hand sanitizers are more effective in denser households. So households that are houses that are small, but have many members in the house. And the reason for this, if you look at the coefficient that's in front of this is negative, and it's significant. And also, if you look at the size of the household, it has to be at least 5 more members. So if both of them are significant, it's essentially grouping people who are living in tiny quarters with many people in tiny quarters, and the treatment effect is more significant in denser households and in non-denser households. And so that's what this thing reveals. And it's we were happy to find this because it was something that the original study authors weren't able to find. And all of this, again, didn't require a correct model for the outcome. And also all of this, you can flip the variable for the flu from 1 to 0, 0 to 1, and you'll get the exact same p-values, which if you follow the original Neyman version, it wouldn't. The p-values would flip again, and that's definitely something that you do not want, at least from an intuitive perspective. The other one is the spillover effect. So for spillover effects, I guess in the simulation I just talked about this, but we tried a couple of different classifiers based on our best understanding of what good machine learning methods exist in this literature and classification in general. Some of these are to demonstrate that having better classifiers leads to better bounds. So we intentionally made P3 to be a bad classifier. So you notice that the bounds are wider than P1, which is our best attempt at a classifier. And so notice that the bounds are smaller, and you can do bootstrap or subsampling to get the confidence bounds for these things. Now, just in comparison, if you did not use any classification, and if you were just to do this naively, the bound for the spillover effect will be 0 to 100%. So it's not very useful. But if you were to use our classification technique, it reduces the bound by 51.2%. In fact, we're currently revising this paper, and there was a suggestion by the referee to make this even sharper by using multiple classifiers instead of just one classifier. And so that actually even reduced this down to another 30%. So it's something that we're currently editing. And I think this technique in general has a lot of attractive powers in terms of combining machine learning and partial identification. So how do we interpret this when you got these results? So from P1, we see that using masks and hand sanitizers can reduce flu case among NTs by at most 49.9%. Combining these classifier results, we think the true NT is mostly likely near 0. That is, it's probably the spillover effect that's going to be tiny to even, for even statistical significance. And some practical tips for getting tight bounds. These are a little bit, these are still given. So using more covariates can obviously tighten these bounds, and that's the difference between these two, P2 and P3. And as we also found out during our revision, as one of the reviewers suggested, we can always improve this bound, not by hoping for better data, but actually by having better classification algorithms. And one of the suggestions was to use a very interesting classification algorithm that even tightened this bound further. And so the PI now has two opportunities to essentially get tight bounds. One is to hope for good data. The other one is to actually train a very good classifier and then really sharpen it as much as possible. So yeah, this is the summary of my talk. So the first part of the talk was focusing on overall and heterogeneous ITT effects. Again, we're not saying this is a big extension. It's just a modest extension of Ding et al. To cluster data, and something that we notice about affine transformation that I think people should be aware of, and some minor theoretical innovations allowing the cluster side to go to infinity, may go to infinity. The second part of the talk was on how to new methods bound spillover effects. Among NTs we focused on, but the paper can also do ATs and COs. And essentially, the key idea is to use a possibly imperfect machine learning classifier to predict these subgroups, and then use that within the linear program to essentially bound, get more tighter bounds and target estimate. All this is model free in that you don't even need a perfect classifier. Whatever classifier you'll give, it will always contain the true effect of interest. Given any classifier, you will get the sharpest bound possible. And then in practice, it really led to significant reductions in practice. And all these methods that we introduce is assumption lean in that none of them, this one does not assume a parametric model for Y, and this one is, you can use a classifier. Again, I should be clear, you can use a classifier that we described above, but we think that's broad enough that it can be satisfied, it can fit most classifiers. And we use standard assumptions, and we also avoid extra assumptions for the sake of point identification. Some future directions, I guess briefly. One is, after this work, we've been actually thinking about how to do optimal treatment assignment. I was actually talking to Alex about this in our meeting, my adventure into optimal treatment regime during COVID times. And one of the things that we wanted to figure out and was of interest to us is, for each cluster, what is the minimum number of units to be vaccinated using masks to get an acceptable public health outcome? And is this rule better than existing approaches based on the SIR model? And we were almost done finishing up this work, and the ideas of this paper actually inspired to answer this question. The second thing that we're also working on a bit more slowly is how to use machine learning to obtain better bounds. So oftentimes machine learning and causal inference is used to obtain non-parametric estimates of a point identified parameter. But if it's not point identifiable, or if you don't want to make assumptions to point identify, how can you use machine learning to essentially make tighter and tighter and tighter bounds, especially in a risk-free way where you don't have to necessarily assume that the machine learning model consistently estimates the nuisance parameter correctly. And so yeah, there's some advice about here. I think I already mentioned it, is to, I think, in my opinion, again, I'm biased, but I think our methods for analyzing ITT effect are very promising. Really relies on less assumptions than it doesn't make a model for Y, especially the model dependence. And to sharpen bounds, if you wanted to use our method to sharpen bounds and NTs, I think you can use our method, and you should probably collect more covariates to really sharpen those bounds at the end of the day. And with that, I will thank you again for your attention.
Thank you, Han-Sung. So we have some time for questions, and I think there are a few. Okay, so I think Marlena raised her hand.
Hi, thanks for your talk. I think when you were talking about the assumptions for the spillover method, you discussed that you can't have any defiers in the population. And I was wondering if, and I think you also mentioned that you could potentially address this with the study design. I was hoping you could speak to that a little bit, and then also whether or not you think that's a valid assumption for the Hong Kong data that you analyzed.
Yeah, so that's a good question. So in the case of, you can, in typical non-compliance literature, you can enforce no defiers by actually not offering the program to the control arm, in which case they will never be able to take up the new program. In the case of the Hong Kong data, because there are free masks and hand sanitizers, technically a person in the household could go out and buy one and then use it in themselves. But the key here is that they would only do that behavior if they're not offered. But if they're offered the free mask, they would actually decide, hey, I don't want to use the free mask, but I would rather buy it myself and if they're not offered. So it is definitely possible to violate that assumption, but we think it's probably unlikely. Also, in the data set, when the original authors looked into this, they actually almost everyone were either never takers, as in they would never take it even if they're given for free, or they were compliers. There are very few always takers who would proactively wear masks in a flu season back in 2008, or they would systematically defy the investigators' recommendations in opposite directions as well. So that's what they found. But I guess in COVID settings that may or may not apply. And not to your point about whether if this is violated, whether the LP program apply, you can definitely violate this assumption. It's just a constraint on the LP, and you can remove that constraint and you can still get the bound as well. So the bound will most likely be wider, and it will probably contain the null effect, is my guess, is how this will proceed.
Thank you.
Yep.
Other questions? No other questions?
I guess I have a few questions. So thanks. I mean, this is really cool stuff. So a few very basic questions, actually. So one, and this is my ignorance, I often see in the context of these kinds of like when there is interference and so on, a focus of the estimand being sort of a finite sample estimand. So you're defining the estimand in terms of these counterfactuals, not of averages of the like sample averages of the counterfactuals rather than population averages of the counterfactuals. So what are the pros and cons of that, and what's the motivation for doing that?
Yeah, this is I think a great philosophical debate that one could have in those causal inference workshops. I think the biggest thing here is one of the advantages of finite sample inference, at least in cluster settings or interference settings, is that you effectively you treat the dependent structure as some arbitrary set of constants, essentially. That has its pros and cons. That is, you don't necessarily have to make a distributional assumption about the covariance matrix structure directly. You can just say that, oh, these are just some set of numbers that may or may not affect the variables, and you just take the suprema of it. And so that's one advantage of it. So you're free from making some modeling choices about how dependence occurs. Now, the biggest downside, I think, is that often because of this, if you already know how the network structure is, it's almost always underpowered. If you compare, especially between some of the econ work that do peer effects versus like the finite sample approaches of doing this, you notice that in the econ world, they get pretty strong peer effects, partly because, if you believe their model is true, they have an explicit model for how people might interact in a market. And that actually helps a lot. Whereas if you were to do a finite sample approach, and at least in its current form, they don't make any assumption that they just treat this as just some arbitrary constants, essentially. And then as a result, the bounds or point estimates or the standard errors are often wide, and it's often doesn't lead to, often, not always, but often does not lead to significant network effects. So those are how I look at it currently.
So you don't think there's any impact on the generalizability of the results, because it seems to be in some sense targeted towards this particular sample? And so is it just that there's extra uncertainty that one would tack on if you were to consider the population averaged estimate?
I think so. I mean, so generalizability, I think, I would think so. You could theoretically say that conditional on your observed values, you could do finite sample inference. And if you wanted to extend the sample average treatment effect, population average treatment effect, you can make a model on how the population relates to the sample, and then the things will roughly carry through. There's like a paper there's an interesting discussion by Rosenbaum and Jamie Robbins in a statistical science paper in the early 2000s. They go at it with each other about which one is correct and which one is incorrect. And I think there's a key quote in that paper which says that Lehman at some point proved that if you make some model assumption between the population and the sample, everything that we do in finite sample becomes the population, and everything that you do in population becomes the sample. So they're essentially almost the same side of the same, they're essentially from the same coin, just in different sides. But it might get more complicated in network sampling settings. One of the things I'm working on in a separate project is snowball sampling, where you're collecting data to discover who are actually infected, especially rare outcomes. And in that setting, this issue that you just raised, it becomes much more pertinent, and you can't just take it for granted.
Makes sense. Another question I had, so at some point you had this this indicator that appeared, and then you said you had to smooth it out and so on, and then you had these tuning parameters in there, and you gave these orders, right? So is that just a technical device, or it actually matters quite a bit for the sake of the answer you'll get, and so is that choice truly? I mean, the obvious question: how sensitive are you, in some sense, to that selection in practice, and how do you select that? If you know the order, you know you're missing a constant in some sense for the selection. So, is there a pragmatic way of selecting this in your approach?
Yeah. So actually in our data, we chose this to be like 0.001 or something, and this to be like log, whatever the smaller order of this thing was. In terms of actual sensitivity, it's not very sensitive to the, the constant in front of this thing, let's say. This device is mainly for theoretical reasons, because partly one of the things that these are all smooth and technical, also differentiable around the region, but one of the nice things about it is that this has an exponential tail, which actually helps with inference for bounds. And that's actually a key reason that we decided to use this. But if you just wanted to get bound without the uniform inference part, then you could, we actually started with these two, and then you can get it. And actually, we even simulated it. And it turns out it's fine, but theoretically, we just needed some of these exponential tail conditions in the tail for this to work, of a specific type of disorder, essentially.
I see. Okay,
Yeah.
makes sense. And last question I had was, and I guess it pertains mainly to the first project, which is, so you said that you could look at heterogeneous effects. And so I guess, one question that popped in my mind when you were presenting the application is, what's the extent to which the effect depends on a particular household size?
Oh, a
And
lot.
for a small household, what's the effect versus a big household? And I would think that would drive quite a bit. And so, is that just a covariate? Is that just a household level cluster level covariate? And so you can just literally include that in there and no problem, it just goes through.
Exactly. Yeah, your intuition is perfect. Correct. In fact, I would even go further, say that people should be including cluster size in CRT analyses. They sometimes do, but the thing is, we only discovered this invariance property of both of this once we started to look at what the role of this thing NJ was. And the cluster size is effectively, you can think of it as a pre-treatment covariate. But the thing is, unlike usual pre-treatment covariate, they don't define the estimate. This one actually defines the estimate, especially when you're averaging across different unit sizes. And so this thing, in short, yes, you're correct that you can put the cluster size and then get the effect of small clusters or large clusters, and then you can get the heterogeneous treatment effect, especially with our affine invariant estimator.
And is that something that was done, to try to see the extent of variation of the effect based on household size?
Yes, so we found in our data set, that denser households are more effective in terms of this mask program than non-denser households. So sorry, I just to click through this a little bit, but we did include the cluster size. In fact, instead of actually doing this as a continuous variable, we actually looked into the literature on infectious diseases, and this is how or at least this is what they recommended that they do, is that at some point it tapers. And apparently 5, or I think it depends on the study, but apparently there's like a threshold at which it should taper. And so there's an n equals 2 as well at the bottom end, and so this is how we coded it. We were initially just thinking of coding it as NJ, as just one continuous covariate, as a naive person myself would do. But then we went a little further and actually studied, okay, like I'm sure people study how diseases spread in small clusters and how did they code this variable. And this was the recommendation that was suggested by at least the references that we found thus far.
So again, just looking. Sorry, I had missed this particular table. So and so if you were to now say below 5 and above 5, so would we expect that basically the below 5 would just be essentially 0? I mean that it would average out close to null effect, and so that is that the point that's being made here, that if it's a large household, then you do expect an effect, whereas for smaller households, is that how I'm supposed to read this?
Yes, so small, dense households. So small households with many people in it. So imagine living in a 500 square feet apartment, but you have 10 people living in that apartment. That is a dangerous, that is where the mask will be helpful. But if it's a large household unit of a mansion and you live with 10 people in a mansion, then it's probably fine.
So it's really an interaction between, you know, the NJ and house size, or some kind of relationship between the.
Yeah, essentially it's an interaction between these.
Yeah.
We could have added an interaction variable here. The reason I don't know why we didn't do it, but I think part of it, yeah, I mean, essentially because these two are significant and the direction of this effect is opposite of each other, then essentially number of people in the household matters, and how big the household matters.
Mm-hmm.
And both of them are significant, at least in a 10% level, or if you wanted to kind of squint a bit, and it'll be 5% level.
That makes sense. That was super cool stuff. Thanks so much.
Yeah, thank you for the questions.
Any other questions? If not, then let's thank again our speaker. And this was actually our last seminar for this quarter. So I'll see you in the fall. Thanks again for giving our last seminar, Han-Sung.
Well, I'm glad to finish it off. And thank you.